Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. So this is a second version of a video I've done, labeled number 2 in this series, on friction, and an experiment that, in my opinion, illustrates that the kinetic energy theorem, that twice the velocity is 4 times the energy, that 3 times the velocity is 9 times the energy, that 4 times the velocity is 16 times the energy, and 5 times the velocity is 25 times the energy, is wrong. Now, I could say it's wrong just because they've never proven any of that 5 times the velocity, 25 times the energy, or 25 times the energy to make something go 5 times as fast. That none of that there's not a shred of evidence for any of that. And I would argue that this simple experiment just basically proves the point that it doesn't happen, that it's wrong, that physics has made a huge mistake in misunderstanding the application of energy. Often can make something look like it has more energy when it doesn't. Okay, you can apply energy over a large surface and it won't do much damage to the surface. You apply the energy in one location, it does a lot of damage. So we can understand a pointy arrow makes the arrow look like it has more energy because it penetrates something easier, but it doesn't have more energy. You didn't put more work into pulling the bow. So there's just those facts that you can be deceived, and so you have to do this science kind of carefully. And this very simple experiment, in my opinion, creates a logical proof that's undeniable by reasoning. Okay, all right. So if you're rolling an object, now let's just say we're doing this in a vacuum, so we're going to eliminate air resistance as any factor. You can understand that we're rolling it and it's going to come to a stop, okay? And something's going to stop it, all right? And that's what we're saying, is that stopping event is where the energy went. So whatever's stopping it, okay, that's where the work is being done. So as much as people don't want to think about heat or vibrations as being work, that's what's going to take place, is that as it rolls, it's going to transfer its linear motion, its energy that's in the form of linear motion, and it's going to grind it into the ground. It's going to knock stuff up. It's going to hit the ground, and if you thought of the ground as being made out of little pool balls or little bowling pins, it's essentially just going to transfer all its energy into these little atoms moving. So instead of one big thing moving, there's going to be a bunch of little stuff moving. And this is the same principle in which Joule is famous for creating a Joule tank, that basically did this same thing, in the sense that it takes the motion of something and converts it into agitating water and increasing temperature via a law, a strict law, that basically allows you to collect all the energy of an event as heat and then just measure the temperature increase. So clearly in this experiment, the 2 velocity object goes 4 times the distance. So it goes to here. So this last 1/4 of the event is exactly the same as this first experiment. And so we know that heat will be the same. The heat here in the ground, the work done on the ground, will be identical to the work done on this ground. Okay. And the simple argument is you have to believe that the gravitational force, which is creating the friction, somehow you have the same force, 9.8 over this 1 second. Let's just say it's in 1 second units, and you have 9.8 on this 1 second. And so obviously the surfaces are getting an apparent, spreading of the force over a much wider distance here than here. And so it doesn't seem very likely that the friction here, here, and here would be exactly the same. So this is their bar of the energy. They're saying the friction is the same, the amount of heat going into the surface is the same. So it doesn't matter how fast I have a scale and I let things go over it with speed, that somehow they aren't going to weigh less. They're not going to put less energy into the scale. And I think we all know, of course, they will. The faster I move it across the scale, the less it's going to weigh, essentially. And it's merely because, yes, it's going to transfer it has less time to transfer its energy. because it's making less contact per unit of time and distance. And obviously I'm arguing that no, the friction starts off quite low because of the high speed, and it gets gradually bigger and bigger and bigger, and that all you're going to get is 2 units of friction. You already know this unit. Again, just understand, you already know how much this is. And the only argument is the friction the same all the way through the experiment? And obviously I'd say it's not. Okay, and this is testable in the sense they could probably roll something like a bowling ball on a surface, and it would create enough compression to create a heat signature that could actually be seen by an infrared camera or something. So it is probably testable. There might be better ways to find out how hot it is, how much friction was how much work was done in the form of friction. And it's just a fact that the heat is the work, because that's what's taking the energy. Nothing else is taking the energy. The only thing taking the energy is the rubbing contact. So as I've pointed out, you can sort of understand if I drop something next to a brick building and then I create a wind or sandblaster or some other force to push the object into the building, you know that it's really going to depend on how much force there is. If there's a lot of force pushing it in, it's going to rub hard and it's going to lose a lot of energy to the building, to the surfaces, rubbing, and the less hard, the less. So just like rubbing your hands, you can do it lightly and create very little heat, or you can do it aggressively and create a lot of heat. And the same principle applies here. It obviously will be less friction here. There obviously will be less heat through this whole pathway. The total heat will be the same, but this obviously will be gradual. It won't be constant. So you won't have 4 units of heat here. You'll only have 2 units of heat, because the heat here is going to be less per inch, and it's going to be the same in quantity as the heat here. So you're only going to have 2 units of heat, which means you only had 2 units of energy. You only did 2 units of work, and it's 2 units of momentum. And there's no room for the kinetic energy theorem in this experiment. It proves it doesn't work. It doesn't predict the outcome. 2 units of heat means there's not 4 units of energy. If I did it with a 3 velocity, it would mean there's not 9 units of energy. If I did it with a 4 velocity, it's going to mean there aren't 16 units of heat or energy in the surface. So it's, in my opinion, for reasonable, fair people, this is a pretty good piece of skeptical evidence to give you reason to be skeptical of their theory. And until they show you something, you really shouldn't be falling for it. You shouldn't say, I'm going to trust them, I'm going to believe them, even though you'll never see any evidence proving it. And that's not good science. It's not good brain function. It's not doing honor to, hundreds of millions of years of animal struggle to acquire the capacity to contemplate such a question. I mean, you're insulting everything to sit there and say you're going to believe this fable they tell you, and you don't need any evidence whatsoever. That's just wrong. That's bad human behavior. So, all right, enough said. So that's what they have to address. They can't do their silly little calculations, their silly little playing with the numbers. They can't just assume constant friction. They have to explain why there would be constant friction when obviously the gravitational pressure on the surface per inch is less. It weighs 9.8 here. It weighs 9.8 on this small surface. We all know that per inch there has to be less pressure. You really must know that. You really must know that if I apply the pressure in one little spot, it's going to be very high. If I apply it over a huge surface, it's going to be very low. All right. So, enough said. Till the next time and such.